Good morning, friends. In last lecture, we had seen the first problem on analysis and design of single reinforced section. In that, we have calculated the moment of resistance. Now, we'll see the next problem, that is type 2 problem, that is analysis type. Again, here FCK, B, D, Fy are given. You have to calculate Mu and AST for balance section. And for that, the following steps are adopted. You have to calculate XU max, then equating Mu limiting is equal to Cu into Z. That is Cu is ultimate compression, that is 0.36 FCK into XU max into B, and Z is the lever arm, that is D minus 0.42 XU max. Since in this section, if the section is overimposed section which are not allowed, so it can be considered balance section, and for that purpose you have to directly calculate XU max and you have to consider the compression side because it is a overimposed section. Overimposed means extra steel is provided, so concrete will crack first. So you have to equate compression side first. For that, the problem is as below. See this one problem. A singly reinforced concrete beam 200 mm and having effective depth 350 mm is reinforced with 3 bars of 12 mm diameter using M15 concrete and Fe415 steel. Calculate moment of resistance of the section. So the given data is B is equal to 200 mm, D, that is effective depth, again here printing mistake, small d is equal to 350 mm, 3 bars are given of diameter 12 mm. So AST 3 into pi by 4 d square, that is 339.29 mm square, M15, that is FCK 15 Newton per mm square, Fe415, that is Fy 415 Newton per mm square. Then first you have to calculate XU max. In type 1 problem you have calculated XU, then XU max, then comparing you have decided the section, that is overimposed section or underimposed section or balance section, and then you are going for calculation of designed moment. But in this case you have to directly calculate XU max. So XU max is equal to 0.48 D, that is 0.48 into D, that is D 350 mm, that is 168 mm. So calculation of XU, that is 0.87 FYST, that is 113.43 mm. Comparing XU and XU max to decide the section. Since this XU is less than XU, since the XU is less than XU max, the section is underimposed section. So if the section is underimposed section, you have to calculate the moment of resistance by equating Tu into Z, and if it is overimposed section, you have to equate Cu into Z, that is Tu 0.87 FYST, that is D minus 0.42 XU. Put all these values and calculate the moment of resistance. This is the first problem. Then second problem, calculate AST required for a RCC section 200 into 450 mm effective to resist an ultimate bending moment of 150 kN. See here bending moment is directly given. You have to only calculate AST, area of steel required. Here number of bars are not given. In last two problems number of bars given, that is AST is given. But in this type of problem you are not given the number of bars or AST is not given. You have to calculate AST. But you have given a bending moment, a moment of resistance, that is 150 kilonewton meter. Assume M30 concrete and Fe415 steel. So solution is, as we had given ultimate moment, that is 150 kilonewton meter, D effective depth 450 mm, then Mu limiting is for steel grade 0.415, for Fe415 is 0.133 FCK BD square, that is Q, that is ultimate moment of resistance for Fe415 is 0.133 FCK BD square, that is 0.133, FCK concrete is 30, B width 200, depth 450 square. That is MU limiting 161.59 kilonewton meter. But actually given ultimate moment of resistance 150 kilonewton meter and the limiting value or maximum value which we can put on the beam is 161.59 kilonewton meter. Since MD is less than MU limiting, section is underimposed section. So for underimposed section, you have to calculate the steel area. You can calculate this steel area by equating XU and XU max or CU is equal to TU. But you can calculate this steel area by using this formula which you have adopted for one-way slab or two-way slab or for cantilever slab. You can calculate by using this formula also. So steel area is 114.66 mm square. This is the problem. The next problem, to design a rectangular RCC beam section to carry a working bending moment. See here, working bending moment is given, not ultimate moment or design moment is given. This is working moment, so you have to apply the factor of safety here. Working moment of 70 kilonewton meter. Assume width is equal to half of D. That is, we have to design the section. We have to calculate the width and depth of the section. This is the fourth type of problem. Use MTPT concrete and Fe415 steel. Check are not expected. For that, here bending moment is given as 70 kilonewton meter, width half of D, M20 and Fe415. There are factor moment. Since this working moment is given, you have to apply the factor of safety, that is 1.5. That is 1.5 into 70, that is 105 kilonewton meter. Then equating this Mu to Mu max, you have to calculate the depth required. This is the required depth for the given bending moment, that is 420.75 mm, say 425 mm. Assuming cover 50 mm, overall depth is 475 mm. Since B is equal to half of D, put the value of D here, that is 212.5, say 215 mm. So the depth is 425 and width is 215 mm. So this is the design of beam. For AST consideration, PT limiting for M20 and Fe415, PT limiting is 0.96% given in the table. So accordingly, you have to calculate the percentage of steel, that is AST is equal to 0.96 divided by 100 into width into depth, that is 877.2 mm square. Provide 3 bars of 20 mm diameter giving area 942.4 mm square. So width 250 mm, AST 3 bars of 20 mm diameter and overall depth 475 mm. This is the overall design of the beam section. So okay, thank you.